What's up, everyone? This is Mr. Stahl, and today we are talking about similar triangles or not. And what this lesson is really focused on is can we determine if two triangles are similar? And what we're going to find out is we're going to have shortcuts, just like with congruent triangles. So if you think back to your congruent triangles, we had side, 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 angle, side, um, angle, angle, side. We even had for right triangles, hypotenuse, leg, right? We had these shortcuts to determine if two triangles were congruent. Well, the same thing is going to happen with similar triangles. But before we start out with that, let's get our warm up done. Our warm up says the first set of three ordered pairs forms a triangle. Determine whether the second three corresponding ordered pairs form a similar triangle. Justify your answers. So right now, if we think back to our last lesson on dilations, we know that dilations form similar triangles or similar shapes, similar figures, right? So if we could show that this is a dilation, then we are able to go and say, hey, these are similar triangles. And we could actually do that here. Why? Because if you look at all of these points, right? Right here, 4 divided by 2 gives me 2. Once again, 4 divided by 2 gives me 2. Right here, 8 divided by 4 gives me 2. 4 divided by 2, as we've been saying, is 2. And the last two are 8 divided by 4, which is 2. And once again, 8 divided by 4, which is 2. So for all of these, when we divide, it's going to give us 2. That's not a coincidence. That's not something that, oh, wow, we're lucky that happened. No, that's happening because these are similar figures. And what happens is we have a dilation here from the center and we're multiplying it by 2. And when I say the center, I mean the origin of a coordinate plane, right? Center of the coordinate plane, origin. We're dilating from the origin by a scale factor of 2. So this is a dilation of a scale factor of 2. So what we're going to write here is dilation from the origin with a scale factor of 2, period. Right, I'm going to make that a bullet point. I just like having bullet points to organize. Right, so that's my bullet point. And what we then know is all relations create similar figures. Create similar. All dilations create similar figures. Awesome. And that's our warm up right here. So we know I just introduced you to a rule that if you're dilating from the origin, all you have to do is take your coordinates and multiply it by a scale factor, right? So if you take all of these original coordinates, 2, 2, multiply it by 2, it becomes 4, 4. 4, 2, multiplied by 2 becomes 8, 4, and so on and so forth, right? So you just multiply, and it gives you the next thing. Now, one thing I do want to add into here, let me go back, keep. Right? The one thing I want to add into here is this picture control, right? This is a picture and an example of what is actually happening here, right? So this picture is this example. We have our first triangle. Let me go back to full screen. Our first triangle here is down below ABC is 2, 2, 4, 2, 4, 4. And then our bigger triangle CDE is our 4, 4, 8, 4, 8, 8. So as you can see, they are similar. They look the same, except one is bigger than the other. Awesome. Fun. So as I said today, our lesson is called Similar Triangles or Not. And what we're actually talking about is establishing triangle similarity criteria. Similarity. Not the easiest word to say early in the morning. So, our learning goals are to establish the following things. We're going to establish angle-angle similarity, side similarity, and side angle side similarity. So these abbreviations are they remind us of our congruency shortcuts, right? And we're going to be able to use these and then use them to show that triangles are congruent or similar. Sorry, triangles are similar. So our first one is our angle similarity. And what it states, it says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So if we know that these two angles are congruent, so for instance, if we have A and D right here, if they're equal, and then we have C and F, and they're equal, then we can say that last step right there, triangle ABC is similar to triangle DEF. So remember, here that symbol means similar, right? So those two triangles are similar. So all you have to say is two angles in this one triangle are similar or congruent to two angles in that other triangle. Boom, our triangles are similar. Awesome. Let's see an example worked out. In this example right here, we have these two triangles, ABC and CDE, right? And we want to know, hey, are these triangles similar? Well, first up, it says, our first bullet point says A and E are congruent because they're two right angles and all right angles are congruent. So let me mark those off in one color. So these are congruent. Those are right angles. That's something we all know. Next one is something we might miss. One thing that we should always do is if we have two triangles that are touching each other, you're probably going to have something congruent, whether they share a side or maybe they have an angle that is congruent. So the next one is angle ACB. So ACB, this angle right here, and that's going to be congruent to ECD. This angle right here. These are vertical angles, right? These two lines intersect, they create these vertical angles. And vertical angles are always congruent. So what do we have here? We have angle similarity, and it tells us that triangle ABC and triangle EDC have two pairs of congruent angles, which means using the angle similarity, these triangles are now similar, right? We could say that they are for sure similar. Awesome. So let's look at our own problem. Right here it says, the triangles shown are isosceles triangles. Do you have enough information to show that the triangles are similar? Explain your reasoning, right? So if we think back, we did learn something special about isosceles triangles. And that special thing is that if we have isosceles triangles, their base angles are then congruent. So we have these sides that are congruent here and here. We can say that these base angles are congruent here and here. But then we can also say that these base angles are congruent. But the problem with these triangles here is we don't know if my green angles are congruent to my red angles. There's nothing to tell me that. And the reason that we don't know that is because, look, LM is a single marker, right? We have a LM, it has that single marker on that side. PQ, that side has a double marker. So we're not told that these sides are congruent either. If so, they would both have a single marker, they would both have double markers, right? That would show us that the one side in the one triangle is congruent to the other side in the other triangle. So unfortunately, we don't have enough information. We can't say for sure if these are similar or not. My guess, guys, kind of look a little different to me. But once again, I also can't prove that without measuring things or finding it out myself. But now we have almost a similar situation. Once again, it says the triangles shown are isosceles triangles. You have enough information to show that the triangles are similar. Now, it basically looks like the same problem we just had on the last slide, except we have one key feature here, and that's that angle T is congruent to angle W, right? Angle T is congruent to angle W. And what I want to show here, right? What I want to show here is I want to pretend like angle T and angle W are 100 degrees. And this is going to help us show why this is a different problem, right? So now, if T is 100 degrees, that means W has to be 100 degrees because they're congruent, they're equal, right? So what we could then say is, oh, well, now we know that this is an isosceles triangle. So just like the last problem, our base angles here are congruent. And in my next one, its base angles are congruent. Now, once again, we don't know if these base angles are congruent to these base angles, but we have information that we could show. Now, one thing we need to think back and recall is that if we add angle T, angle S, and angle U together, it should equal 180. So, right, angle T plus angle S plus angle U equals 180 degrees, right? But one thing we know is that angle S and angle S is equal to angle U. So what I'm going to do is swap out this angle U here for another angle S. We're going to say angle T plus angle S plus angle S equals 180. But another thing I could do is I know what angle T is equal to. We're going to, actually, I'm just going to go back and erase it here and go 100 degrees equals angle S plus angle S plus angle S equals 180. So what I'm going to do is bring that 100 over. We're going to subtract it from both sides, do some algebra here, right? That's going to give me angle S plus angle S equals 80, right? And that really is like 2 angle S equals 80. We divide by 2 on both sides, and we get angle S equals 40, right? So angle S equals 40 degrees, but then we know that angle U has to also equal 40 degrees. Why? Because angle S equals angle U. Whew, that's a lot of words, right? Let's take a break. But once again, what did we do here? Let me just go through these steps again. We said that these three angles inside the triangle have to add up to 180, right? My next step, swapped out angle U with another version of angle S. Why? Because angle S and angle U have to be equal. The reason I wanted to do this was so later on I can combine it, right, and make 2 angle S, right? And you only need one variable, and we're thinking about these angles as variables right now, right? I also, in that second line, swapped out T for 100 degrees because that's what we said it was equal to. I just made that number up. This is an example, right? Then we solved using our algebra. Now, the thing we could do, and the thing we could look at is my next problem here. Whoops, sorry guys. We could look at the next problem, the other triangle, and we could actually do the same exact thing. We could say angle W plus angle V plus angle X equals, once again, they have to equal 180 because it's a triangle. Once again, we know that angle W is 100 degrees. Plus, I'm going to say angle V plus angle V equals 180. And why am I able to do that? Because we know that angle V, angle V is equal to angle X. Right? They're congruent, so they're equal. If I swap it out, and again, what could we do? We could subtract 100 from both sides, right? And that gives me 2 angle V. I combine like terms. I just did that same thing here. Equals 80. So we divide by 2, and we get angle V equals 40 degrees. Just like our other one, we now say 40 degrees. And what do we have? We have actually angle, but we have that angle, right? So we can now say by angle similarity, actually I'm going to shorthand it. Angle similarity, triangle CUS is similar to triangle WX. So because of angle similarity, these two triangles are similar. And we just had to do some work to get there. But notice how this problem with that one little piece of information at it, that T and W are congruent, with that little information at it, we are able to prove that these are now similar. Awesome. Let's move forward. That's our angle-angle similarity. Now we're looking at side-side-side similarity. Now this one is a little different because so far with all of our triangle congruency shortcuts, we said that things were congruent. Angle-angle similarity, we said these two things are congruent. With side-side-side, it gets a little different because now it says if all three corresponding sides of two triangles are proportional, then the triangles are similar. So we have to actually think back to something we learned yesterday. So yesterday I talked about the word proportional, or 2 days ago, right? But that lesson before this, we talked about proportional in our dilation lesson. And what that means is we have ratios that are equal. So if we look down below, I can show you what that means. I'm going to actually highlight these sides in different colors so we understand what's going on. So AB is over DE, right? Those are the corresponding sides of these triangles, which means they're the sides that are in the same spot of each triangle. So we're going to set those up as a fraction. And then we're going to set up another pair of sides as a fraction, BC over EF. Right? BC over EF. Green sides. And last but not least, AC over DF. Boom and boom. Now, what would happen if these triangles are similar? All of these fractions will equal each other, right? So for instance, they might come out to be a half each, right? They might all equal a half. They might all equal a third. They might all equal 2/5, right? They may all equal 7 over 2. They may all equal 5, right? Maybe they come out to be whole numbers. But they're all going to be equal, and that's what it means to be proportional. Another fun thing about these fractions is this is going to give us our scale factor that we were talking about yesterday with dilations. So they all wrap up into the same thing. Now, if you don't fully understand this yet, just by looking at this picture and looking at the thing down below, that's fine. Let's go to an example, and that might help you out, right? Sometimes actually going through a problem and seeing it in action, you're like, oh, and seeing with numbers helps you out a little bit. So let's go look at that. So it says determine whether triangle UVW is similar to triangle XYZ. If so, use symbols to write a similarity statement, right? So what we're given is measurements of all our sides here. So obviously that tells us it's a red flag. It says, hey, try to use side similarity, right? But Mr., how do we do this? That's what you might be thinking. How we're going to do this is we're going to look for our smallest numbers on each triangle, right? I'm going to write these ones in red. So I'm going to underline them. So 24 is my smallest on this triangle. 16 is the smallest on this triangle. And let's set those up as a fraction. So 24 over 16. Now, this is something where we have to think back to maybe 7th, 8th grade, maybe before that, where we have to simplify fractions. And I know a lot of us don't like this, so I'm going to kind of tell you how I think about it. I always go the easiest route. I mean, for me, it's the easiest route. Maybe for some people, it's not. And I divide by the smallest numbers, and I might do it over and over again. So both of these numbers are even, 24 and 16. So I know they could be divided by 2. So 24 divided by 2 is 12, and 16 divided by 2 is 8. Now in my head, I have this fraction 12 over 8. And I'm like, oh, both of those could be divided by 2. So 12 divided by 2 is 6. 8 divided by 2 is 4. I messed that up. Sorry, guys. I'm dumb. Oh, wait, no. 6 and 4. I didn't mess it up. I'm not dumb. Haha. 6 and 4. When I said it out loud, I said it 6 over 4, but when I was thinking it in my head, I was thinking 4 over 6. Whoops. It was 6 over 4, right? Once again, they could be divided by 2. So 6 divided by 2 is 3, and 4 divided by 2 is 2. So this is really going to simplify to 3 over 2. Now you might be like, oh, what? I really divided by 2, divided by 2, divided by 2. Another way we could think of this is as follows. 24 divided by 8 gives me 3. 16 divided by 8 gives me 2, right? We're simplifying these fractions. Find the top and the bottom by the same number. And it simplifies it. So it simplifies it by 3 over 2. So what this is telling me is that if we want these triangles to be similar, the other two fractions have to simplify to 3 over 2. So let's take a look. Next, I'm going to go my next big number in each triangle. This one right here, 33, and then 22. So I'm going to put 33 over 22. And these numbers are usually easier to spot, right, when we have something like this, because it's the same number twice in a row. It's 33, 22, right? Which means that they could be divided by 11. Right? So we divide both sides by 11. 33 divided by 11 gives me 3. And 22 divided by 11 gives me 2. Right? So now, once again, 3 over 2, 3 over 2. We're on the right path. The last one has to give me that 3 over 2 right here. 36, 24. 36 and 24. I have to say, hey, what number can they both be divided by? And once again, you could think it out in twos, right? You could go say 36 divided by 2 gives me 18. Divided by 2 gives me 9. Can't divide 9 by 2, but I could divide it by 3. 9 divided by 3 gives me 3, right? Top I'd have 3. And then you just follow the same pattern down below. 24 divided by 2 gives me 12. Divided by 2 gives me 6. Divided by 3 gives me 2. Or in other words, we're dividing the top and the bottom by 12. Right? Divide the top by 12, bottom by 12. That's what we're doing. Because really, what we're saying is we divide it by 2, we divide it by 2, then we divide it by 3. Right? In my original sequence, 2 times 2 is 4, times 3 is 12. Works out the same way. But the major thing here is when we simplified each of these fractions, it gives us 3 over 2, which means that all of these, these are proportional. They're all equal. Let me do that in a different color, right? They're all equal. So since all these things are equal here, we could say that we have side similarity, which means triangle UVW is similar to triangle XYZ. We used our side similarity. Once again, this is different from what we've been doing because we're not saying that these sides are congruent, right? Obviously, 24 meters doesn't equal 16 meters, right? 33 doesn't equal 22. 36 doesn't equal 24. Obviously, these triangles are not the same size. They're similar, right? They're the same shape, different sizes, which means that their sides are proportional. So if we put one over the other, and we do that for each pair, they're going to equal the same thing, right? So 3 over 2, or 1.5, right? 3 divided by 2 would give me 1.5. 1.5, 3 over 2, that's my scale factor for this situation, right? Awesome. Let's move on. Last one, we have our side angle side similarity theorem. And now this one says if we have two corresponding sides of two congruent triangles are proportional and the included angles are congruent, then the triangles are similar. So for this one, the sides that we're talking about here, I'm going to underline it like in the first one. We have red, we have A, B, and D, E. These sides have to create a ratio, right? And they have to be proportional with the ratio of AC, DF. AC, DF. But we don't have the third ratio here. What we have in this one instead is that included angle, which means the angle between these two sides. So right here, A and D those angles will be congruent. So we have side, angle, side, side, angle, side. But the important thing is that that angle is sandwiched in between those two sides, right? Let's look at an example problem for this one right here. So once again, I'm going to do it all by colors. I like to organize with colors. Go to your smaller sides, 12 and 8. So I like putting the bigger number on top. So I'm going to put 12 over 8. And once again, we have to simplify. Both of these could be divided by 4. So divide by 4, divide by 4. Funny thing is, this could both come out to 3 over 2. This is just a coincidence. It's not always going to equal 3 over 2. I know the last problem did also. It's not always going to be the case. Just a coincidence. And then we're going to go to our next one. Our next side, 24, 16. 24 and 16, we say that 4, 16. And both these could be divided by 8. Right? And once again, it gives me 3 over 2. So we know that those sides are proportional. So really what I could do is write it down here, something like this. I could say that AB over FD, name of the sides, is equal to CB over FE. Right? That's what we could technically say, which means that they're proportional, right? When you write it like this and say that two fractions are equal like this, it means that those fractions are proportional. And then we also could see here that these angles in between our sides are congruent. So we can say that angle B is congruent to angle F. So what do we have here? Side, angle, side. So we could say by side, angle, side, similarity, triangle A, B, C, similar, triangle D, F, E. Amazing. Just like that, we use our side, angle, side similarity. And with that, our lesson is over. We had an example of each of our similarity and similar ratios. So what you guys have to do now is either ask questions if you're confused about any of it, watch another video on it, and get to work on your practice problems. So good luck. If you have questions, make sure you ask. And I'll talk to y'all next time. Peace out, everybody.